First of all, I would like to thank Professor Chipchuk for this kind invitation to come to Poznan. This is not my first day in Poznan. The first visit goes back to the year 1989. There was a conference in function spaces. I was very much impressed by this conference at that time. Sometimes during lunch, I had to share the table with Luxembourg and Sickel, persons which are important for me in some sense. During the dinner party of the conference, even Orlic showed up. So it was impressive for me to take part. And later, I have been several times here. Several times I took part in this series of conferences. So for me, it's quite a nice place. Today, I would like to talk about this topic. All you know characteristic functions. And there is a so if this is my domain E, I'm interested in the associated characteristic function, or better to say, on the smoothness of this function. And switch off the light. Okay. Yeah.
No. It even better. It was better than okay.
It's good now. Okay, that's really okay. Sorry, no problem. So it's clear that those characteristic functions may have, in a certain sense, different regularity. But what are, say, the main properties of the boundary, of course, one has to study to understand this regularity. So if you think on the standard spaces one knows from the basic courses, then these are no longer helpful. Of course, if you start with a subset of RD measurable, of course, with finite positive measure, then such a function always belongs to LP for all P, and it does not belong to first order Sobolev spaces. And of course, it does not belong to spaces of Hölder continuous functions because it's not continuous. So we need different spaces. And in some sense, my talk today will be a little bit propaganda for Besov spaces. There are spaces of fractional order of smoothness. So let me recall some classical notions. So of course, all you know the Lipschitz condition. We need to have an estimate of the first order difference of a function f uniformly in x and h. So the shift h is given by h, and we study whether such an inequality is true with a general constant L. And Hölder condition is just a generalization. We replace the absolute value of h by the absolute value of h to the power s. So I always consider this on the whole space. So x and h are from Rd. And then in 1951, Nikolsky had the idea, let us replace a supremum, which could I have written here, by an integral. So he asked for an estimate of the LP norm of the first order difference in this form. And he introduced spaces, say f from LP belongs to the nowadays called Nikolsky-Besov spaces and sometimes simply Besov spaces, if and only if this quantity here is finite. So these spaces will show up during all over my talk. And S should be here between 0 and 1. It makes sense for S equals 1, but then the spaces defined in this way would change their meaning a little bit, so there's a different definition. One has to increase and the order of the differences, but higher order differences will not play a role during my talk, so I will skip this. So let me first start with some examples. My motivation to study this question, regularity of characteristic function, has at least three different sources. The first source has been more complicated. In the 90s, I was interested in pointwise multipliers for Bezoff spaces. That means the question whether a given function has the property that all products of this function f with functions from a given Bezoff space lead to a new function belonging again to the same Bezoff space. And one of the basic questions is the case that you consider the characteristic function of a half space, because traditionally the half space is part of the way you have to cross when you try to understand spaces on domains, but you would like to carry over properties from the space is defined on RDs, and the half space is the first step in between. So it was of certain interest whether the characteristic function of a half space is a pointwise multiplier. That was my first interest. My second interest has been, so during my academic career, I've given many lectures, basic courses, advanced courses on approximation theory. And then it's quite natural to consider spaces defined as follows. So usually approximation theory is a little bit simpler when done in the periodic case. So T just means a torus. So the periodic function with identification on, say, a basic interval minus pi pi. So if you introduce spaces like follows, you take all f in L1 such that the supremum n to the s, f minus, and SNF denotes the Fourier partial sum of order n in LP. That should be finite. So S, of course, is a positive number, and here the supremum is taken over all natural numbers, including 0. So these are quite natural spaces, approximation spaces, and the outcome are, again, these Bezoff-Nikolsky spaces, but the periodic case, which is not much different. So the periodic case is just a subclass of the corresponding non-periodic case, in a certain sense. So I'm very much interested in if and only if assertions concerning the regularity of characteristic function. And the first one is very easy to get. So we need to study these two sets. To each shift h, we consider an appropriate set E of h. Oh, I have forgotten to say, capital E refers always to a non-trivial subset of RD. Non-trivial means not empty and not equal to all of RD. And then we study the case that x belongs to E, but the shifted version does not belong to E. In f of h, vice versa, x belongs to the complementary set of E and x plus h not. And remember, in the definition of the Bezoff spaces, we have to study the LP norm of the first order difference with respect to the shift h. And then it's easily seen, because if x and x plus h belong to E, it's 0, and if both do not belong to E simultaneously, it's also 0, that you get an identity here. This is just the sum of the methods E of h and f of h. So very easy. And then you get a first theorem. Let E be a set of finite measure, then the characteristic function belongs to LP, of course. P should be any number between 1 and infinity. Infinity, P equals infinity could be treated as well, but it's not interesting. And S should be between 0 and 1. This is given, or these restrictions are coming from the definition of the spaces. Up to now, I've only given a definition for S between 0 and 1, and then we get this is true if and only if the sum of these two measures taken to the power 1 over P times the absolute value of H to the minus S. This remains bounded, uniformly bounded for all H with absolute value less than or equal to 1. So I'm always interested in examples, but here what concerns examples, this condition is of limited use because it's quite easy to use it as a sufficient condition, but the necessity to show necessity by using this condition is quite difficult. However, let me start with a few examples where you can use it. So first we consider the circle, or we could take a ball in RD and the rectangle or generalized rectangle in RD. And then you see I've drawn a shift of this basic domain here of the ball. And what we need to do, we need to calculate the volume of the dotted area in both cases. And then it's easily seen. So the shift would be a vector of this size here in this direction, or here you can see it better from one corner to the other. Then the volume is equivalent to the length of the shift. And using the criteria from the slide before, we immediately get that the characteristic function of either a ball or a generalized rectangle belongs to such a Bezoff space if and only if S is limited by 1 over P. So it's well known that these Bezoff spaces are monotone with respect to S, and this means that this space with smoothness 1 over P, integrability P, and here infinity is something like a limiting case for these two typical domains. So of course the ball is a C infinity domain, and one could conjecture, okay, to a C infinity domain should be associated a characteristic function with maximal regularity. In the first step, it's only a conjecture, but it's indeed true. For that reason, I will call S equals 1 over P the limiting case. A real explanation for this will be given on the next slide. But before, I need to introduce new spaces. So Bezoff was a PhD student of Nikolsky, and in his PhD thesis, he introduced more general spaces, not only 2 parameters, but now 3 parameters. There is an additional Q. So we have to compare the LP norm of a first order difference of F with a quantity absolute value of H to the power minus S, but we replace a supremum in front of by an integration. So it's not difficult, it's a few lines to show that this construction has the following properties. These spaces are monotone with respect to Q. If Q is growing, is getting larger, then the spaces are getting larger. So usually Q is called a fine index. In the French school, people call it the microscopic index, indicating that Q is less important than S and P. And indeed, if we change S, then we get for free the choice of the third index. This embedding here is true for all Q, not only for Q equals infinity. So in this sense, Q is less important than S. So by using this, it's not difficult by considering this first result here. If you have a ball in RD, then a locally integrable function satisfying that the integral with respect to b taken over the first order difference multiplied by 1 over the absolute value of h, if this limit exists and is equal to 0, then the function u must be constant almost everywhere. So that can be used very easily to in the context of characteristic functions. And then as a simple consequence, it shows up the following. If we ask, are there sets E in RD such that the characteristic function belongs to one of these spaces, B1 over P, PQ, with Q less than infinity? Then the answer is no. There is no such subset. So this means that B1 over P, P infinity RD is the best what we can get as long as P is fixed. And this has been proved by Willisashvili already in the 80s, almost. It was a little supplement by me. So to make clear that that there are very simple arguments behind. So in the first moment, it looks like here we have an L1 condition. Here we have an LP condition behind. So we need to ask, what is the relation? But the relation is just equality, because this quantity takes values 0 and 1, nothing else. And if you take it to the pth power, nothing is changed. So it's not complicated. So now I need a more complicated notion. I would like to turn to the problem, which quantities are helpful to understand under which conditions on the boundary the corresponding characteristic function has its maximal regularity here. So I need the parameter of a set. So the parameter of a set E is the following quantity. We have to take the Lemus inferior. H to the d minus 1 means the Hausdorff measure in dimension d minus 1. Mj is a sequence of sets with smooth boundary or polyhedra, approximate such that the corresponding characteristic function approximates the characteristic function of E in L1. And this is the boundary. So we take in 2 dimensions, it would be in 2 dimensions, it would be just a generalized version of the length of the boundary. In 3 dimensions, it would be a generalized version of the surface. So if E is nice, that are just the surface or the length. And then there is an interesting, nice formula known since the 60s. It says that the norm of a function f in BV is just an integral over the parameter of these level sets. Here BV is, of course, not defined in the classical way. This is defined in the distributional sense. So you require that the first order derivatives in the sense of distributions are measures with a finite total variation. And this is also the term you need to calculate the norm. And if you apply this formula in case of a characteristic function, it's immediate that you get the characteristic function belongs to BV if and only if the parameter is finite. So this is a main quantity here in this context. But is there a relation between BV and the Bessev spaces? And there is. So the way how this can be derived is known for a long time. Hardy Littlewood for d equals 1, Guliszashvili for d larger than 1. If E is a measurable set with finite measure, then the parameter is equivalent to the behavior of the first order modulus of smoothness taken in L1. So it's well known that Bessev spaces can be characterized by the behavior of modulus of smoothness. But this here concerns a limiting case. So it does not lead to a characterization of a Bessev space with integrability 1 and smoothness 1. To get such a characterization, we had to take here a second order difference. So there is a little technicality behind, but however, it allows to switch to Bessev spaces in case of characteristic function. And then the following quite nice characterization takes place. So if E is a non-trivial set in Rd, P is between 1 and infinity, without infinity, then the following assertions are equivalent. So we have this maximal regularity of a characteristic function if and only if the parameter is finite of the set E. So this is the main geometric condition. So the equivalence of the first two with the fourth condition we have seen on the slide before, and the equivalence of the third condition and the fifth condition we have almost seen. We have to take P0 equals 1. Then this can be proved in a few lines, this equivalence. And so the remaining arguments needed here are also not very complicated. But we get the following. So if you have a BV function, if you have a characteristic function which belongs to BV, at the same time, it belongs to all Bessev spaces of this form. So with smoothness, S equals 1 over P and Q equals infinity. There's some sort of robustness with respect to Bessev norm. So this has been known since the middle of the 80s, more or less. Guliszashvili himself, he studied characteristic function as pointwise multipliers. He did not much care for membership of characteristic functions in those spaces. So examples, first example, that looks more complicated than it is, please. The definition of elementary Lipschitz domains looks a bit technical, but look at the last condition, and for the remaining you remember this picture from basic courses. We take an interval AB and we take a Lipschitz function, which is, say, positive on AB. This is a picture for d equals 2. And for d larger than 2, we have to replace the interval here by a cube in Rd minus 1. So this is a definition. So, and it's not difficult to show that these elementary Lipschitz domains, they lead to characteristic functions of the maximal regularity within this context. And the way you prove this is you just estimate these sets E of H or the volume of these sets and prove that this behaves like the size of the shift. So then there is an almost trivial corollary. We take the union of the closures of a finite number of pairwise disjoint domains, E1 to En. And then the assertion is that if as long as these E1, as long as this characteristic function associated to E1 to En are elementary Lipschitz domains, or there are rotations, translations, or reflections of those Lipschitz domains. The set E itself has maximal regularity. So what is behind? So if this is E, then you can glue together those characteristic functions of subdomains. And this is, in principle, the characteristic function is just the sum of the characteristic function subdomains. So this argument is true as long as the boundary of the character of these subdomains have measure zero, but this is easily shown. So, and the Besser space is a Banach space, that means in particular linear. So there is another conclusion from this corollary. If you try, or it's almost impossible to draw a picture of a set such that the corresponding characteristic function has not maximal regularity. Because when you try to draw something, then it's always finite, and you cannot draw, say, you cannot draw a domain with a fractal boundary. So here are some examples. This polyhedral cone, this is an elementary Lipschitz domain. You just turn it around and you see it better. But these two, there are cases which are covered by this corollary. So you need to introduce a certain decomposition into elementary Lipschitz domains. But this is easily done, also in case of this icosahedron. So these are all examples of domains with maximal regularity. So here, the Astrid is an example I've always treated in my basic courses. Of course, this is not a Lipschitz domain. So it's not Lipschitz if you look for this figure in for d equals 2, then it's not Lipschitz in these 4 points. But of course, it has finite parameters. So the length of the boundary is finite. So the corresponding characteristic function has maximal regularity. And if we take the rotation, then the number of points in which the boundary is not Lipschitz is infinite. So it's along the equator, it's not Lipschitz, in the North Pole, in the South Pole. But the surface is finite, of course, the contents of the surface. And here's a further very simple example. A family of domains in R2 with a parameter epsilon. So it's like square root, it looks like this. So it has finite parameter. That means the corresponding characteristic function of this yellow domain has maximal regularity, but the Hölder regularity of the boundary can be as small as possible. So Lipschitz continuity of the boundary is sufficient for maximal regularity of the boundary, of the characteristic function, but it's not necessary. Vice versa, there are cases with almost, with minimal Hölder regularity, epsilon as small as we want, such that the corresponding domain has maximal regularity. So there's a big difference between regularity of the boundary in the traditional sense and regularity of the corresponding characteristic function. So that was an introduction. Now, from the mathematical point, more interesting case will be considered. What about S strictly less than 1 over P? So first, I would like to recall a well-known necessary condition. So for simplicity, we take a bounded domain, then the characteristic function belongs to the Bessev space for some S positive and P and Q between 1 and infinity, requires that the volume of the Lebesgue measure of the boundary must be 0. So a domain with a property that the characteristic function, the associated characteristic function, has some positive smoothness, cannot be too wild. So the boundary need to have measure 0. It must be a null set. So those conditions have been known in the literature since the middle of the 90s. There's a booklet by Jafar and Meyer. They prove similar assertion by using the notion of the packing dimension in the middle of the 90s. So later on, also Farago and Rogers considered those questions, but they were dealing with quasi-balls. So sufficient condition. If you remember this set E of H, that was the set of all X in E such that the shifted version does not belong to E. And you search for estimates from above of this volume, then it's very natural to consider the delta neighborhood of the boundary given by this definition. So it's some sort of a pipe along the boundary. And then it's clear that the volume of E of H is dominated by the volume of this delta neighborhood, where delta has to be larger than or equal to the absolute value of H. And in this way, it's very easy to derive the following sufficient condition. So S need to be strictly less than 1 over P. That comes into play because we are working in the background with characterization of Bessev spaces by splines. So a well-known topic in your country, I should refer to the early works of Ciesielski and Sickel from the 70s. And there is a paper by Ropela also in the middle of the 70s. But here we need only the most trivial case. That means we approximate with piecewise constants. And then it turns out that the following quantity here is sufficient. I've forgotten to notice in some cases I do not need the full delta neighborhood. I need only this part which belongs to E itself. And then one can show that if this integral here is finite, then the corresponding characteristic function belongs indeed to this Bessev space with parameters S, P, and Q. Later on, I will need the case if Q is equal to P, then you see the power here is 1. This I will need later on. And this condition here is an immediate consequence of our earlier result of the theorem 1. Probably you remember there was a characterization using these sets E of H and F of H. So there's a number of results with respect to sufficient conditions concerning membership of those characteristic functions in Bessev spaces. There's one by Strichhardt from the beginning of the 90s. Jafar and Meyer I've already mentioned. There are several contributions by Triebel, also one by Schneider and Vibiral, and also the contribution of Farago and Rogers with respect to quasi-balls I had already mentioned. So I said before, I'm interested in if and only if conditions. So it took me a while to think about if and only if condition in this context. So I need dyadic cubes, and I need only those dyadic cubes with measure less than or equal to 1. So with the corresponding characteristic functions, one can characterize Bezoff spaces as long as S is strictly less than 1 over P. So there are characterizations using the best approximation of a function by, say, characteristic function of those dyadic cubes. And then it turns out that the following is indeed a characterization. The characteristic function of E belongs to the Bezoff space if and only if this complicated quantity here is finite. So the beginning of this quantity, this is like in this case I have mentioned, so the characterization by best approximation. So, but this quantity here replaces the best approximation. We have to compare each dyadic cube with E. So we need the volume of this intersection, and we need the volume of the intersection with the complement of E. And this is a difficult point, we have to take the minimum. If it would be the maximum, it would be easily estimated from below and above. But in case of the minimum, the estimate from below in concrete examples turns out to be very complicated. So this characterization, as the first characterization we got in theorem 1, looks again nice, but it's hard to apply in concrete examples. So for introducing different necessary conditions, I need the notion of weakly exterior Sickel domains. So there are many notions to characterize some sort of regularity of domains. So in 2008, in a book on wavelets, Triebel introduced the notion of a Sickel domain. This is based on the Wisner decomposition of E. So the Wisner decomposition is of a given domain is a collection of dyadic cubes having specific properties. Those which are relevant for this context is that the decomposition is done into cubes having the properties that the distance of the cube to the boundary is proportional to the length, to the side length of the cube. And all cubes have to be inside the domain. So with those cubes, we are working in this definition here. A non-trivial domain E is said to be weakly exterior Sickel if there exists constants such that one finds for any interior cube Q a complementing exterior set. It needs to be not a cube, it needs to be just a set contained in the complement of E and a point x0 in Q, satisfying that this exterior set is not too far away, is just in a ball with center in x0 and radius a certain multiple of the length of the side length of the cube. And this set should be sufficiently large. That means the volume should be larger than or equal a certain positive constants times the volume of Q. It's maybe more instructive for looking for this picture here. So this is a Wisner cube. That means the side length of Q is proportional to the distance, and these equivalence constants, they are independent on the specific cube. And then we ask whether this set QE is in this ball and whether it is sufficiently large. And in case I need it, I will indicate here the dependence on the domain E by writing B sub E and A of E, A sub E. Aha. Probably once I need the the notion weakly interior Sick, then you exchange the roles between E and the complement of E, and weakly Sick means weakly exterior Sick and simultaneously weakly interior Sick. And then one can prove the following. There's even an inequality behind. So I can estimate the homogeneous part of the Bersov norm. This is just this quantity as we have seen before without an LP term. And you can estimate this by a product of these powers of the constants B of E and A of E times this quantity here, which we have seen before in theorem 4 with the case Q equals P. And in theorem 4, we had an upper estimate in a certain sense, so a sufficient condition. And here we have a lower estimate. Both together leads to the following if and only if characterization. We need to know a priori a certain regularity of the domain. It should be bounded and weakly exterior Sick. Then, under these conditions, the characteristic function belongs to these specific Bersov spaces with P equals Q, if and only if the delta neighborhood or the part of the delta neighborhoods of the boundary which are inside of E satisfy this condition. So by the way, for those who know, there's a scale of function spaces very often treated parallel to the Bersov spaces, namely Lee-Hawking-Triebel spaces. And you could replace this BSPP here by FSPQ, where Q is arbitrary, and the same would be true. So there's a generalization to Lee-Hawking spaces in this case. So there is an earlier result by Farago and Rogers for quasi-balls. Quasi-balls are in particular those bounded weakly exterior Sick domains. So the most important example in this context is a snowflake domain. I hope you have seen it before. So the construction starts with an equilateral triangle. Then you decompose any line into 3 equal parts. You throw away the middle part and you put there a new equilateral triangle. And that is done on each line, and then you continue, you iterate. And here my computer has stopped after 6 iterations, so he could not do more. So, but this is a snowflake domain, and the boundary is, of course, a classical von Koch-Core. This is a standard example for a fractal. Oh, this one. And what is known, so the Van Koch curve has a fractal dimension. Here I've used 2 of the most popular. Hausdorff dimension, Minkowski dimension coincides. It's logarithm 4 over logarithm 3, so it's strictly larger than 1, expressing in some sense that the boundary is quite complicated. So the boundary is in no point differential, for instance. So it's really complicated. But on the other hand, the boundary has locally in any point the same regularity. So which is not so easy is that the snowflake domain is a Sick domain. But at the very beginning, when I started to deal with this problem, I had the hope that the notions, the well-known notions concerning these fractal dimensions will match my problem. That means that I have an if and only if correspondence between regularity of the characteristic function and those fractal dimensions of the boundary. But this is not true. It works only in one direction, so in directions of efficient convergence. So a real proof of this has been given in a recent paper by Cayetano et al. In Journal of Functional Analysis. But An idea how one can do that is indicated also in a book of Triebe from 2008. And then the following is true. By introducing this abbreviation, S sub 0 is 2 minus logarithm 4 over logarithm 3. Here, the 2 is replacing the dimension, d equals 2. Then we get the following. The characteristic function of the snowflake domain belongs to this Besov-Nikolsky space if and only if S is less than or equal to S0 divided by P. And the characteristic function belongs to BSPP if and only if S is strictly less than S0 divided by P. So there's a little difference. Here, equality is admissible, here, not. And these Besov spaces here, they can be replaced by Triebeli-Sorkin spaces where Q is given for free. This is still true, but there are a few remaining cases that will not cover membership of the characteristic function for all values of Q, but for some at least. So there are very few further domains with fractal boundary where one knows an if and only if condition. In most of the cases, one knows sufficient condition. So now I would like to turn to, just a moment, to the problem, do we really need this condition here? What we really need is some sort of restriction. This is probably not the most general one. And for that reason, I have introduced, in some sense, a generalized Nicodim. Oh, here the M is missing. I'm sorry, Nicodim domain. What we take this rectangle and we take away this strip. And you see this strip becomes more and more narrow. So maybe it's more instructive to explain the details of the construction by looking at the intersection with this line here. So we have two types of sets, A0, AJ and BJ, and we require that the intersection of AJ with this line, or the length of the intersection, is proportional to the length of the intersection of BJ with this line, is j to the minus alpha. And the alpha is a given parameter larger than 1, and gamma is a parameter even larger than alpha. So the distance between BJ and AJ plus 1 should be equivalent to j to the minus gamma. That means more narrow than this one here. And for this example, it's possible to show, first of all, these sets, depending on these two parameters, they do not fulfill the regularity condition from our previous theorem. But we have a control of the volumes of the delta neighborhoods. They depend on alpha. So the concrete dependence is not of relevance, but they depend on alpha. And then one can prove just by hand. It's a rather long and not quite nice calculation that the following is true. So the Minkowski dimension of the boundary, this depends on alpha as the volumes of the delta neighborhood of the boundary. The Hausdorff dimension and the packing dimension, they are just one. So there is no relation to alpha and no relation to gamma. But the regularity within the framework of these Besov spaces, they depend on gamma. And again, we have a difference between the case Q equals infinity. There we have the condition that S times P has to be less than or equal to 1 minus 1 over gamma. And for the remaining Q, there must be a strict inequality. That shows that there exist domains where the behavior of the volume of the delta neighborhoods has practically no relation to the smoothness itself. So if we want to have a relation of the delta neighborhood, of the volume of the delta neighborhoods to the regularity, we need an extra condition. And within these extra conditions, this weakly exterior Sickel condition is probably only the first attempt to understand this. So that's all what I wanted to say. Thank you very much for your attention.